necessarily an angle theta. And the vector product of A and B gives us a vector that's 90 degrees to the plane that makes up the two vectors. And the magnitude, a little bit of this is repeat, but it's needed where I'm going. AB sine theta, and this is magnitudes of each vector. So here's the parallelogram. And the vector C equals vector A cross vector B. This is called the cross product. Or vector product. In this case, this is a vector. Those are all vectors. C, which I've written there, is AB sine theta, that's the magnitude. And the only difference between that and this is this has magnitude and direction because it's a vector. This is just magnitude. So when it says cross product, I mean that's the word cross in that comes from A cross B. Let's look at a simple example. This is in 3 dimensions, X, Y, and Z. And let's have a vector B here. Vector A. A and D are both in the XZ plane, so the cross product can show up in the Y direction. And later we'll see practical applications to this cross product, what it's actually doing in terms of mechanical and structural engineering. This has a magnitude of 45, let's say, and A has a magnitude of 60. And the directions are indicated. This angle here is 25 degrees between B and A. This happens that B is aligned on the x-axis. They don't have to be, but we have that's on the x, and then A is 25 degrees toward the Z in three-dimensional space. And they're both on the x, y, x. So C is going to be like this, because it's going to be always perpendicular to the plane that makes up those two vectors. And we have C is A times B, these are magnitudes multiplied by the sine of theta. So C is 60 multiplied by 45. And the sine of the angle between them, which in this case is 25 degrees. So we get 1,141. So it's actually, that's 45, 60 is quite a bit taller than is indicated here, right? Space, like word. So now I'm just looking down on the x, z plane. So this is x and this is z. And then y would be coming out of the page. So the line, this is 45, this is 60, and the angle is 26 degrees here. This area, so I'm going to take this and extend it like this. So it's a parallelogram, and then this is horizontal. Let's try that again, almost horizontal. Okay, and then the area that is made up, this area here. Equal to C, which is 1,140. So it's the area of the parallelogram. It's made up by these vectors. Triad, X, Y, Z, right? I put my thumb in the X direction, my first finger up there, and my third finger follows the Z. So it's a right-handed triad. It's like our IJK. And let's say now we have, this is B, is 50. And I have A, is 30. In this case, they're lying on the X and Z axes, so it is 90 degrees between them. And we can go like this. Let's look down on it. So it's area. We're going to get C here, right, in that direction. So perpendicular, in this case, it's going to be a line kind of wide again because the E and A vectors are in the X, Z plane. So let's look down on it. There's X, Z, Y coming out of the page. And you can see it looks like this. There's B, 50, here's A, 30, and we have this. And then in this case, this is 90 degrees. You can see it very clearly here, right? And you look down on it, and you have a C. Is AB, and the sine of theta. Sine of 90 is 1, right? So this just becomes A times B, which is clearly the area, right? So we have C. Let's put here sine of 90 degrees. 1, so this is just A. 30 multiplied by 50 by 1. So just 30 times 50, and that gives us 15. So the advantage of the sine theta is it doesn't just work for 90 degrees. It's not just A times B as an area, but if it's at an angle, it also gives you the correct area. Let's say you have a vector like this, another vector like this. This is 100, and this is 100, and you have an angle theta between them. You can see this time is not 90 degrees. And the area that's formed, you take this vector, put it here, like that. And so it would be this area, right? And it would still be the area is 100 times 100 multiplied by the sine of that angle. Without the sine theta, it would give you much too much area. And this length is 100, this length is 100 because it's forming a parallelogram. I'm taking this 100 and putting it there, taking this 100 and putting it there. Right? That's again, X, Y. Oh, I didn't put the value here. This is 1500. X, Y, and Z here. And again, in the XZ plane, I have, in this case, this one's 100. This one next to it is also 100, similar to this. And the angle between them, start of the origin, is only 10 degrees. So they're coming closer and closer, right? Rather than 90 degrees or 45, they're 10 degrees. So they're almost aligned, but they're slightly off each other. And for this, we get C. This is a B and A. So C is AB sine theta. Magnitude is 100 times 100 is a sine of 10 degrees. $1,736. That's this value here. So C is AB sine theta, which is the, that's not right. Wrong angle, it's this angle. It's the angle between the vectors. And let's see, to understand that, this is a magnitude B, so it has a length of B, this is A. And this vector projected horizontally out here would be B times cosine theta, but the height, this is B sine theta, right? This is B, magnitude of vector B times the sine of theta. And so to understand why that's the area, you can imagine taking this and it's like this, and slicing it, right? A bunch of times like this. So you got these little little rectangles, and we slide them all over like this so that they're 90 degrees now. Like this, right? So this is still A. For each little sliced part, it has a width of A. I slide it over, and the height now is B sine theta. And so you can see now this is the area. After we've done that, cut it, slid it over, and so again the area is just this times the width times the height when it's drawn like that, which is equal to let's say area A, which equals C equals A times B sine theta. So I mean, it's as simple as that. That's where it comes from in terms of the magnitude. AB sine theta. Let's make it a little smaller. The angle between them. So you have X, Y, and Z. Now I have, let's say B is 90. And A is 110. The angle between them is only 0.1 degrees. Not 1 degree, 0.1. So they're almost right aligned with each other. We have C is AB times the sine of theta. So 110 multiplied by 90 times the sine of 0.1 degrees. So for this, you see it gets smaller, right? 17.3. So now we have this little c. The other ones I didn't have enough board space to show it, but C was, you know, this is 50, this is 30, this is 1500. That was way up there, right? And then same with the other ones. Now this is smaller. C is getting smaller as the two vectors are coming into alignment with each other. Okay. So finally, let's look at this. Again, we draw X. C. And I have my 90 here, and my 110 right along the same line. They go right on top of each other, one's a little larger. So in that case, theta is 0. So the angle between the vectors is 0. We have C is AB times the sine of theta. Sine of theta, sine of 0 is 0. So we have C is, this is A and this is B, just like that. Or the other way around. 90 was B, 110 was A. So I have 110. Same thing as this, times 90. Multiplied by 0. So that zeroes out the whole thing. Therefore, C is 0. So we have this, and then C is 0. There's no magnitude, okay? So in this case, there's no effect in that direction. And when we see practical applications, you'll understand why and how that can be important in certain situations. And you can also see that the area of the parallelogram that you would draw here, it's closing like this, it's getting narrower, and then finally there's no area between the two vectors, right? And that's because C is 0, so it's all consistent. Area equals 0. You can see that just on inspection. Okay? As the two vectors get closer and closer, like this one, the parallelogram, 0.1 degrees. If you extend this out, extend that, and you're getting narrower and narrower area. When you bring them together like this, and that's it, and you have no area between them and no C value. Here I have, also in the XZ plane, I have A, vector A, which is 50. And I have vector B, which is 75. And there's an angle between them of 25 degrees. But in this case, looking down from Y, A and B are switched, and so C is going to go, instead of the positive Y direction, it's going to go in the negative Y direction, the magnitude of the direction of the vector itself. And that has to do with, remember we said, if you stand at the top of C and look down, you should get a positive rotation, a clockwise rotation from vectors B to A. And here, if I stood up here on Y, if the C was in this direction and I stood up there and looked down, I would see the opposite, right? From B to A, it would be rotating counterclockwise. We can sketch that here. So if we drew, say, X, C, this is Y, I'm positive Y, I'm up above it. I have A, this is A, B, this is 25 degrees. You can see if I'm up above, looking down, going from B to A is counterclockwise, right? And so that tells us C is actually like this, in the opposite direction. So if you now stand up there in this direction, so let's draw like this, X. Now I'm at the end of C, looking back down to the origin. I have X, I have Z this way. All right, and then this is Y coming out, or actually going down. So now I have B like this, which is 75. And A, this is 25 degrees. Now, when I look at it from this point that way, I see this, right? And now it's rotating clockwise from vector B to vector A. That defines which direction C goes. The magnitude of C is AB sine theta. So that's 50. 75 sine of 25 degrees. Down. It's down because normally, let's say B is given first and then A, so in that case C is up. In this case A is given and then B. So it switched the direction of C.
It's Wednesday? No. It's Sunday. Having a job's kind of fire, bro. Having a job's fire. You want anything? Yeah. Yeah. Getting to spend money, bro. Shit's fire. Shit's fire. I don't have a job. No financial. Wait, what? I don't have a job. I have financial. Oh, yeah, true. Like, you get them refunds? Basically the same shit. Nah, having a job, it's gas, dude. Like, as much as I hate going into work, once I get paid, like, I'll do it all over again. You know what I mean? I thought, I'd just be broke. Broke, get on Medicare, get on EBT, yeah, you get on financial aid, federal program, you're good. Not good. You just get paid for school. Which is fire. Which is fire. You're in the military? sell your soul with for a couple years. Free income. Dude, after this summer, I don't think I'm ever taking summer classes again, bro. This shit's you got Nico. You got Nico for when I'm. Oh no, yeah. After this is 26 though. Why? I'm never doing this shit again. Okay, what if I do? Maybe definitely. Only one though. Only like one a summer. We gotta graduate. Right? Yeah, that's true. Super duper senior.
So here we have the unit vectors again in the x, the y, and the z directions equal to 1 in all three directions. K is I cross J. So we have the cross product that we're starting to talk about. We haven't seen direct applications yet. But you have K is 90 degrees to this plane, right? And its magnitude is 1. So K is equal to I cross J. So we take the cross product of I and J, and we get the magnitude, which is the same as AB sine theta, but it also gives us the direction. The cross product gives us the vector. And the vector is equal, since this is 1 and this is 1, and it's 90 degrees, right? So the magnitude is 1, but it also gives, the cross product is different than AB sine theta because it also gives us the direction. So we get the direction and value. That's little k. Little j is k cross I. That's the cross product also. And that's, now we're using k cross I. They're 90 degrees and we get this. And we get I is j cross k. example. K is 1. So if we go up on C here and look down, we see this. We see I, which is our A vector. We see B, this is equal to 1. D, which is our J vector, which is 1. And C is coming this way, so now we're looking from here. And you can see that this is 90 degrees. And it's going clockwise from B to A. So that's the correct direction of C. If we had it, if we switched A and B, then it would be going in the opposite direction. Now let's look at J, is K cross I. And C is AB sine theta. So I have I, which is equal to 1. J, no, K. And this is C, which is J. And then looking from above, we have, so from the top of C, looking down on it, I have B. Oh, this is I. So this is B. K. C, you can see this is 90 degrees. This is C coming up, which is J. That. So this is 1 also. Oh, I cross I is 0. That's because if you have the vector I like this, and then the other vector is a line, right? We have the value C is AB sine theta. And so this is I also. So we have, this is 1 times 1 times the sine is 0. So therefore, C is 0. This is 0. So these two vectors are aligned, and so the magnitude, the cross product gives us the direction and the magnitude. But we know from this that we have C is 1 times 1. Let's put it here. So this gives us, for the cross product, we have C is A cross B. This is the vector. But if the magnitude of the vector is 0, the vector itself, the whole vector is 0. And so because of this, we have, this is I, this is B, or I. So anything crossed by itself, any vector like J cross J will be 0, K cross K. So we have I cross I is 0. J cross J will be 0 for the same reason. The two vectors are right aligned. K cross K is 0. We have I, and what we've seen is some of these little sketches over here. I cross J will give us the vector K. So I and J are in the same plane, and K is 90 degrees to that plane. That makes up the IJ vectors. These IJ and K vectors are all unit vectors. K cross I is J. J cross K is I. These are all unit vectors. It's giving us directions, not magnitudes. Magnitudes are all 1, so you multiply that by another vector, it doesn't change the magnitude. But what's interesting is if you reverse these, so that's I cross J. Now we have J cross I is minus K. That's because we reversed the A and B vectors to B and A, and so the C vector, instead of pointing up, is now pointing down for the reasons I gave you before. If you stand below and look back, then it's rotating in a clockwise direction between B and A. And for that same argument, so instead of you get a vector that's going up in the positive direction, it's going down. And then you can, the same exact argument here for all of these. So this is where linear algebra, vector, and matrix math is a little different than regular math. You know, in regular math, if you have A times B is equal to B times A. When you have vectors, A cross, which is like times A, cross B is minus B cross A. You get a negative. Okay, and so then the same thing here. We have, I'm going to switch the order of the vectors. I cross K is minus J. And K cross J. Again, all unit vectors. This is minus. All right, and take a break. C is A cross B, and let's do a parallelogram here. That. So that's this area. This is C the vector, this is C the magnitude, and this is A the vector, and B the vector. If we take a line like this, so this is B and A, and then we say like this to this point, we call this B prime. Then we could draw this A here, parallel to this, another parallelogram, and then I'll hatch it like this. Those two areas are the same, and we still get, so C is that, and
Just very good everything.
so this is A cross B, but it also equals A cross B. Those areas are the same. So the value of C is the same. B here or B some other. But this B prime, you can see in order to intersect the parallelogram, it's longer. So it's longer, but at a different angle. Yeah.
Can you kind of explain the B prime? Like, is it like
Yeah.
a resultant between A and B, or?
No, it's if you take A and put it there, and then if you instead of B being here, you extend the line where it intersects. So it's longer, it's a longer magnitude at a different angle, and yet you still get the same C value. So instead of here, it's starting from the same point. I have this angle here, so if I extend this out where it intersects this line, that defines, completely defines.
So you just moved B down and extended
Not,
the line?
I rotated it, not moved it, yeah.
Or rotated it down
And then
clockwise?
it made it longer.
Until it intersects with A, the
So
other
it
A.
intersects the extension of A, moved over there, yeah. That's how, and then it's the same. It's because the two areas are the same. This area and then this area end up being the same. These are all vectors. So these are C equals A cross B, those are all vectors. A is a vector, B is a vector, C is a vector. And then C can be written as this is A, vector, and this is B, vector. All right, A cross B, C is A cross B. But A can be written like this. And then this A sub x, A sub y, and A sub z, those are just numbers. They don't have direction. They have magnitude. Okay? And it gets direction from these unit vectors. And then the same with B. I, J, K are unit vectors. That gives direction to each of these magnitudes. And Bx, By, and Bz are just magnitudes or scalars, scalar quantities. They have no direction unless they're multiplied by something. That gives it a direction. So these are the components of vector A. And the x, y, z directions given by these unit vectors. Each one of these unit vectors, it has a direction, but it has a magnitude of only one, right? So for each of these components, this gives the magnitude and this gives the direction. The I doesn't really have a magnitude other than one, so it doesn't change the magnitude to something else because it's multiplied by it. But it points it in a direction. This gives it the strength or magnitude of it in that direction. Okay? So this defines completely vector A and vector B. A sub x, A sub y, and A sub z, those are that's just scalar quantities. And then I, J, and K are the unit vectors, each one with magnitude 1 in the x, y, and z directions, or three mutually perpendicular directions, I, J, K, all 90 degrees from each other. And then on the B vector, this Bx, By, Bz, those are scalars, those are the quantities. When you multiply those by the unit vectors of I, J, and K, they give it the appropriate directions. Now we're going to use some of the stuff that we wrote on the board before, which will help us, this information over here, as we'll see. So we're going to multiply this out now, and it turns out that we can eliminate some of the terms that are multiplied by each other in this vector multiplication, because if you have any that have I cross I, for example, that goes to 0, right? And we know that. Remember, as the two vectors get closer together, so the I and I are parallel, so they have no value. We know that ahead of time. And if anytime we see J cross J or K cross K, we can make those go to 0 too. So we can simplify this. See if I can have a better pen. Okay, I get to try to make the trash can.
Oh.
That's close. I can't just throw it hard because it lands there. So the cross it's like multiplication where we have two bracketed groups, so we can multiply all the terms by each other, right? Like a regular math, let's say an algebra problem, and you have 3 terms and 3 terms. So you have to multiply this by those 3 terms plus this times those 3 terms plus this times those 3 terms, or other way, right? It's like having 2 terms in a bracket squared. You have to multiply them all by each other, then you can collect any like terms. But in this case, we can collect like terms, but we can also cancel any that we know are 0 rather than carrying them forward. Okay. So what we get from this is, better math. A sub x times I cross B sub x times I plus So this here becomes a sub x, I'm just multiplying this by this one first. So this is a sub x times b sub x. That's just the quantity, right? Like 3 times 6. And then it's I cross I. Well, we know, looking here, because they're parallel to vectors I cross, the definition of I cross I, that has to go to 0 because AB sine theta, 0, 1 times sine is 0. So this is 0, therefore this whole thing is 0. Okay, so that's the first term. And then the next one, plus a sub x I, a sub x, and I cross, now I'm doing that one, e sub y, and k. So that's going to be, I'll write it like this, a sub x, b sub y, minus I cross j. A sub x, b sub y, that's just sub back. So we got an I cross j there. And so all of these terms, these crosses will be these values here, pluses or minuses. And then plus, the next one, a sub x I, cross product with b sub z, k. That's a sub x, b sub z, I cross k. Yeah, that's the first 3. Then we have 6 more, right? Then we have to do this one, multiplied by those 3, and we're going to do them all. Okay? Plus, let's keep going. Now I'll start with a sub y times j cross b sub x I a sub y, b sub x, j cross I. See, j cross I, that's going to be not a k but a minus k. So we're going to use that. Plus a sub yj cross b sub y j. So this is going to go to 0 because this is ay dy minus j cross j. J cross j is 0, so this whole thing goes down. One, two, three, 4, 5, 6. Okay, so plus ay j cross this one bz k. So this is ay bz j cross k. Okay, how many do we have? We have 3 more, I think. 1, 2, 3, 4, 5, 6. So now we go to the last 3. Plus az k cross bxi. So that's az bx k cross I plus az k cross byj plus azk cross J. This one is AZ, BZ, K cross K. So that goes to 0. This whole thing goes out. So now let's go back. We have here, this is AX, BY, multiplied by I cross J. I cross J is just K, right? So we replace I cross J with K. So plus, this is AX, BZ, I cross K. I cross K is minus J. Plus AY BX times J cross I. J cross I is minus K. Plus that, so we got that goes out. So we're going to this one, AY, BZ, J cross K. That's I. Plus AZ, BX, K cross I. That's J. Plus this next one. AZ, BY, K cross J. That's minus I. How many do we have? 1, 2, 3, 4, 5, 6. That's right. Because we eliminated 3, right? 1, 2. So we had 9. AX BYK minus AX BT J, so I'm putting the negative in front now, minus AY BXK plus AY BZI plus AZ BXJ minus AZ BY I. So let's see if this agrees with this. So now what we're doing is separating all these coefficients with the unit vectors I, j, and k, right? Anything that has I, j, and k. So for I, we see AZ, BZ. Where is it? I have AY, BZ. Oh yeah, that is AY. AY, BZ. So that's this. Minus AZ, BY. AY, BZ minus AZ, BY. They're both multiplied by I. So those are the two I's. The J's, I have, there's a minus, here's a positive. So the first one should be AZ, BX. Okay. Minus AX, BZ. AZ, BX minus AX, BZ, all multiplied by J, right? So that's okay. And then K, positive and negative, so there's AX, BY. Yes. And it should be AY, BX. That's right. So all of these terms now have been brought together. Anything that's multiplied by the unit vector I, anything by the unit vector J, anything by the unit vector K. So then these magnitudes are going in the same direction. So are these two. So are these, right? Defined by the I, J, and K unit vectors. So these are the coefficients, rectangular components. So these aren't vectors, these are just have magnitudes, so they're scalars. So the component in the x direction, AY, BZ minus AZ, BY. In the y direction, AZ, BX minus AX, BZ. And in the z direction, AX, BY minus AY, BX. Or, and this is a vector too. C equals I, J, K, AX, AY, AZ, BX, BY, So, the way you find a determinant of a matrix is take you look at the top row, so you take I, for example, I multiplied by, and then it's this times this minus this times this. So first you take this one, okay? And then, so I times that minus that times that. So that's AY, BZ.
What do you say again, bro? Where you at? What do you think?
Minus AZBY. I'll write it the other way around. This, okay, minus BYAZ. Minus J. So AYBZ, this times AYBZ minus BYAZ. And then minus J, so you go across. And now it's this times this minus that times that. So it's minus J. No, sorry. You have to exclude, hang on, let me fix this. Okay, so when it's I, then you use these two rows down here, or those two columns, I should say. Now when you're over in J column, you can't use the column below it, the numbers. So here we didn't use AX or BX, so now minus, this is finding the determinant of the matrix. So minus J, so now for this, we're gonna skip this column just like we skipped this column. So then it's gonna be A, like that. So this number and this minus this number and that, like that. And it's gonna be confusing the way I've drawn it. But okay, so minus J times, and then it's AX, BZ minus BX AZ. And then it's plus K. So now you come over here and you ignore the column underneath there. And then it's this times this minus that times that. I'll say it again in a minute. Again, so then it's, I'm a K, so I'm not using the numbers below K. I'm going to use those, the AX, BY, minus BX, AY. And then we should be able to see that it's the same thing. So if you look up here, you have I. This is your unit vector I. There's AYBZ minus, this is just written the other way, BYAZ, which is the same, it's just constants. Which is BYAZ is the same as AZBY. That's fine. Minus J. So this is a positive J, so those will switch. We have AXBZ, there's a minus, so that's okay. And then we have minus BX, minus the positive BXAZ, B positive BXAZ, so that's correct. And then we have here K, and AXBY minus AYBX, BXAY. So, in other words, we started with this, right? And then we went through and we simplified. We had 9 terms, and in the end, it shows this is identical, so you can just write it like this. That whole, it's reduced down to this, the determinant of this. Okay? Now, was this clear?
That's easier, yeah.
What? That's easy.
That way's easier, yeah.
Yeah. So okay. So anyway, so just to make sure anyone's not familiar, so when you take a determinant of a matrix like this, you have 3 rows and 3 columns. You go across the row, you have this times
that, so that I times bracket, this times this minus this times this, so this times this. So you just don't include this, and then it's minus, it's always minus, the second one minus j. And now you don't use these two numbers, it's this and you go across, this times this minus that times that, and then it's plus. So it's this minus this plus k, and then you don't include these, and then it's just this times this minus that times that. Right?
All right.
Is it times? Okay, perfect. Problem solved.
All right. Oh.